thanks to MD for the introduction. I'm going to talk about so sort of two aspects to my talk. The first is to talk about some classical identities, and the second aspect is Lie algebras. And I hope to sort of make some connections between these and talk about how some identities come from the study of Lie algebras. So let me begin by talking about some classical identities. So what I'm going to do first is to write down a matrix which I hope most people would have encountered. So I'm going to write an n cross n matrix whose entries look like this: 1 z1 z1 square, z1 to the n minus 1, 1 z2 z2 square, z2 to the n minus 1, so 1, where z1, z2, zn are some variables. And of course, this is what's called a van der Waals matrix. So I'm sure people have seen this before. So this is called a van der Waals matrix. So named after van der Waals. Not sure if it was necessarily discovered by him, at least according to Wikipedia. But van der Waals is a French mathematician who lived somewhere in the 1700s. Now, so what's my identity? You write down a van der Waals matrix and you compute its determinant. Okay, and determinant, of course, by definition is, you have to really do this process. You expand the whole thing out. You get lots of terms, and you sort of add them all up. And the identity says the answer can be concisely written as a product of the differences of the parameters zi minus less than or equal to, right. So all pairs ij which are such that I is smaller than j of zi minus zj. Okay. So the van der Waals, here's the identity I'm talking about, the van der Waals, an identity for the van der Waals determinant. Now, so what I'm going to do next is really some nice manipulations. So let's fiddle around with this a little bit more. So notice one aspect already. This is what we usually call a sum equals product identity. So on the left hand side, the determinant is really a shorthand notation for a very long sum, right? You expand the whole thing out, and the right hand side is a product. So this is a sum equals product identity. Now I'm going to fiddle around with the product side a little bit more. I'm going to just rewrite this in a slightly different fashion. So let me do the following. I'll make each all ij. Okay, I pulled out the leading zi and it looks like 1 minus something. And now notice that because of I is smaller than j, this product really has z1 minus z2, z1 minus z3, z1 minus z4, and so on. There are several z1s. Z2s, there will be fewer z2s in the first term and so on. So if you finally work out what powers of zi you get, so the right hand side, so I'm now working with the product side of the identity. So the power of z1, so notice there will be n minus 1 terms in which the z1 occurs in the first term. So it's z1 to the n minus 1, z2 to the n minus 2, zn minus 1 to the 1, zn to the 0. So that's those are the terms, and then the rest is of course things of the form 1 minus something. So that's the product side of the identity. Now let's ask. So assume here, of course, zi's are all, let's say, complex numbers. In order to divide by zi, I will assume zi's are all non-zero. Okay. So now here's the question. So here's this leading term z1 to the n minus 1, z2 to the n minus 2, and so on. Where does this appear? On the left. So if you are attempting to compute the determinant of this matrix, what term is this? The diagonal, right? This is exactly what you get when you multiply the entries along the main diagonal. So notice that the entries along the diagonal, the product of those is exactly what's over here. Okay. Now, and what are the other terms you get when you do the determinant? So recall, if you are attempting to compute determinant of any matrix, n cross n matrix, what's one way of writing the determinant out? Determinant of A is really the following. So again I'm confident most of you would have seen this the full expansion. The determinant of A is actually a sum over all permutations. So here Sn is permutations of numbers 1 through n. And what is the, well, sign of the permutation? So let me write as sine sigma times, well, what do you multiply out here? It's going to be, so I'm not sure everyone can see this. Summation sigma minus n sine sigma, and then you should sort of pull out a generalized diagonal, meaning from each row you pull one entry out from each, you pull out n entries such that there is one in each row and one in each column. Right. So for example, from the first row you pull out an entry which will, the column number is say sigma 1, A2 sigma 2, AN sigma. Right. So this is the sum you will get when you expand the determinant out, and there are actually n factorial terms because that's the order of the group. Okay. So that's how you would do a general determinant. Now here let's work on the sum side of the identity. So the left hand side, which is the determinant, is that n factorial term sum. And what does it look like? Well, it's just the sum over all permutations, sign of the permutation times, and what are those terms there? So what is A1 sigma 1, which means first row sigma 1th entry. The first row looks like, sigma 1th entry in the first row would look like z sigma 1 power n minus 1. So this is just z sigma 1 to the n minus 1, z sigma 2, n minus 2, and so on to the 0. Okay, so that's exactly what the determinant looks like. And notice that each term is, it's more or less like this leading term. It's like the diagonal, except you apply a sigma to it. Okay, so it looks sort of like z something to the n minus 1, something to the n minus 2, something to the 0, but except that the indices have an applied sigma. So let's rewrite this as okay, and let me say I will think of this resulting thing as sigma applied to the monomial z1 to the n minus 1 by which I just mean z sigma 1, z sigma 2 and so on. Okay, so this is the sum side and that's the product side of the identity. So our identity says that this sum equals that product. Okay? And I've just done this so that there is a little bit more of a symmetry. So this term here will now play a role. So let me just do one further manipulation. So I'm going to manipulate this just a little bit more to get it into a form that I want. So I'm now going to change variables. So instead of variable zi's, let me take new variables xi's, call it where zi's are e to the xi's. Okay, and now of course I assume that the z's are non-zero, so I can always find such x's. Now what do these two things now start looking like? The sum side of the identity now becomes the sum over all permutations sine sigma times sigma acting on this particular object. So which is sigma acting on, so let me call this, okay, so what is this? Z1 to the n minus 1 is e to the n minus 1 x1. Z2 to the n minus 2 is e to the n minus 2 x2 and so on. Okay, so it's e to the sigma acting on this whole thing. Okay. So I haven't done anything yet, and this number here, this particular combination of all the x's, let me call it rho. Okay, it's again some number, just this particular combination, the thing which comes from the main diagonal. So this is now summation sine sigma e to the sigma rho, sigma acting on rho. So given any n complex numbers x1, x2, xn, I can manufacture a complex number called rho, which is this combination, and I can compute this sum sine sigma e to the sigma rho. Okay. So that's the sum side of the identity, and the product side becomes, well, the leading term is again a rho, right? This was the same rho that we had, and the product is now overall 1 minus e raised to the xj minus xi. Okay, where I now and the classical identity that we know is that these two are equal. So here's the identity. You can think of the identity for the van der Monde determinant. Okay, just written out in a slightly different fashion. So let me just record that last line alone. So here's the identity, sum e to the sigma rho. Now I am going to put all the rho terms to one side. So I am going to push that leading e rho to the sum side of the identity, and there is no product e to the xj minus xi, where of course implicitly rho depends on what your xi's are. Okay, so that's the van der Monde identity now, written out in a slightly different form. Okay. Now I'm going to talk about the second part of my title, Lie algebras. And I'll more or less do this by example. So let me take matrices again. So I began with a matrix. So let me consider the following set: n cross n matrices with complex entries of trace 0. Okay, so I've taken all n cross n matrices of trace 0, and so firstly, what's the dimension of this space? So observe, as a vector space over the complex numbers, n square would be the dimension of all matrices, and since we have one condition that the trace should be 0, it's n square minus 1. Okay, so it's an n square minus 1 dimensional vector space, and so of course, if you think of it as vector spaces, that's all there is to it. But I want to think of it as an algebra, meaning I want to define some kind of operation on my matrices. And so here's one operation which is relevant to this. Suppose you take two matrices A and B. One defines the bracket of AB to be AB minus BA. Okay, so that's the operation that's how you multiply two matrices in some sense. I mean the bracket operation. And so first thing to observe, of course, if A and B are n cross n matrices, the result is an n cross n matrix. But more than that, it's actually trace 0. So observe, trace of AB minus BA is actually 0 for all matrices A and B. Right? This is one of the first properties of trace one studies. Trace of AB is trace of BA. So therefore, this fellow always has trace 0. Okay? So what does that tell us? It tells us that this space is closed under the bracket. If you pick two trace 0 matrices, for example, you don't need to start with trace 0 matrices to get this. But from the point of view of saying this is closed under the operation, you start with two trace 0 matrices, you compute their bracket, the result is also in the same space. Right? So definitely this space here is closed under this bracket. So let's give this a name. So this is usually written S L N C, the special linear Lie algebra. So this space is closed under the bracket, and the Lie algebra you can think of as just being sort of a more general structure which is equipped with a bracket operation like this. Okay. So what are the other properties that the bracket satisfies? So observe that SLN C is closed under this bracket operation. And the bracket operation satisfies two other axioms, which I won't necessarily go into. They're called skew symmetry and the Jacobi identity. So in general, a Lie algebra is any vector space which has a bracket operation satisfying two axioms, okay, which are skew symmetry and the Jacobi identity. And this guy is a Lie algebra. Okay, so this fellow is a Lie algebra. So what are examples of matrices which live inside this space? So what kinds of matrices would certainly be here? So there are sort of three main types which you can quickly write out. So let me look at this. So I'm going to construct obvious examples of matrices. So one is U, which is all matrices which are strictly upper triangular, meaning to say on the diagonal and below the diagonal they are zeros, and their only entries can live strictly above the diagonal. So this is strictly upper triangular matrices. Surely they have trace 0, because you are demanding that they are 0 on the diagonal, so the trace is definitely 0. Okay, that's one space. Similarly, you can consider more trace 0 matrices by doing sort of the opposite. You take things which are 0 on the diagonal and above the diagonal, and can only have non-zero entries below the diagonal. So they are called the strictly lower triangular matrices. And well, the third category is, of course, you take purely diagonal matrices. So let's consider matrices which only have diagonal entries, 0 both above and below. But can I take all diagonal matrices? No, because I want, remember I'm trying to construct trace 0 ones. So well, I should only take diagonal matrices whose trace is 0, okay, such that trace is 0. So there are three obvious types of matrices which live inside SLN. They are the strictly upper triangular, strictly lower triangular, and traceless diagonal matrices. Okay. So these are obvious examples, but more than that, they pretty much give you everything. Well, in the sense that any matrix which is in SLN can be decomposed into these three parts. Take an arbitrary trace 0 matrix, you can only, you can form three matrices out of it. Keep only the diagonal portion, keep only the stuff below the diagonal, and keep only the stuff above the diagonal. So in other words, SLNC can actually be decomposed into these three subspaces. Okay, it's what's called a direct sum of these three subspaces. And there are obvious bases. So L itself here and U, there are obvious basis elements. So let me construct some basis for U. Well, you take what are called the elementary matrices. Right? You take Eij, means there is a 1 only in the ijth position, zeros everywhere else. But what's the property that I and j should satisfy for it to be an upper triangular matrix? You will want I to be smaller than j, right? So when will something be in the upper triangular part? Only if the row is smaller than the column. Okay, so take all such fellows, Eij's, where I less than j, they will all be in U. There will be a basis for U. Else will have a basis consisting of E, well, the transposes of those fellows will be here. I'll still call them I less than j. Okay, so here's a basis, and diagonal elements, of course, if you want, you can also write a basis for the diagonal elements. But for now, I just want to keep these. And so here's sort of the next thing one does in order to understand SLNC as a Lie algebra. Meaning to say you want to understand the bracket operation. Then one way of going about it is to try and understand brackets between a nicely chosen basis for SLNC. So you can pick a basis for SLN, and then if you understand how every pair of elements in the basis, what their bracket is, then that tells you what the bracket of every other pair of elements in the Lie algebra is. So it's somehow, it's kind of enough to understand brackets between basis elements. So one really needs to understand, so in order to understand SLNC as a Lie algebra, one needs to understand brackets between bases, or I could also say it this way. I need to take how, here I've firstly broken it down into 3 spaces. I need to understand how things in D bracket with things in D. What would they give you? What would brackets of things with D with things in L give you? And what would things with D in things in U give you? And similarly, U, L, U, and so on. I guess I'm only missing one more, right? L. So every pair, if I understand what their bracket is, I understand everything. Okay. So I need just to understand all these special brackets. And so let's just do it for our EIJs. So at the moment, I'm not going to worry about these. I'm only going to keep D as somewhat sacred and figure out how D commutes with all the other guys. So what's the bracket of D with itself? So let's pick an element, call it x1, x2, xn. So I'll take a diagonal element of trace 0 and ask how does it commute? I mean, what's its bracket with something in U? Okay, so this, you should think of this as trying to do the calculation D with U. Okay, so we're trying to figure out how D and U commute. So x with Eij, and similarly, what is x bracket with Ejis? So this is trying to figure out how D with L, what are those pairs? And D with D is the easiest of the lot. If I have 2 diagonal matrices, then AB minus BA is always a 0, right? So 2 diagonal matrices always give you bracket 0. That's an easy calculation, so I don't need to care. One only needs to understand how things D's and U's interact, how the D's and the L's interact. Okay, now the D with the U, x with Eij, so you just have to do the calculation. Take a diagonal matrix, take Eij, calculate x Eij minus Eijx. You just do matrix multiplication, and you will find this is xi minus xj times the matrix Eij. When you do it with L, you will find that this is just xj minus xi. I mean, it's the same calculation, of course. Ejis. Okay. So I have all this data here, and so here's the point that I want to make. The identity that one has there has some of the ingredients for that identity actually appear when one tries to understand the Lie algebra SLN. So for example, notice that the xj minus xi's that appears on the product side of that identity also appears here. I mean, at the moment it just looks like a strange coincidence, but this in fact goes deeper. So it appears there because it appears here in some sense. Okay, so this is this appears there, but also the question is, what about the sum side of the identity? So there is a group, the sum on the sum side of the identity, the sum runs over a group, and here the group is the group Sn. Now, in general, so observe that the group Sn actually acts on the space of all diagonal matrices. So by this I mean it acts. How does it act? Given a permutation, it takes the diagonal matrix and just flips the, whatever permutation it does to the numbers, it permutes the diagonal entries in the same way. So the space of diagonal matrices always has an action of the group Sn. So in a sense, here is the reason why this this thing is true is because it says something about the Lie algebra. Okay, so here are the two. I mean, here's the two things. So let me just mention the thing in general. So here's the more general way of obtaining such identities. If you could find a Lie algebra just like SLN, if you could find some Lie algebra, let me call it G, which has a similar structure. Okay, so it's a special class of Lie algebras which are called the finite dimensional semi-simple Lie algebras. Finite dimensional words are semi-simple Lie algebras, and SLN is one such example. Whenever you have such a fellow, it always has a decomposition like this into sort of the lower triangular, upper triangular and diagonal portion. And then there are two ingredients. There is always, the first thing is you attempt to find out how these various things, what the brackets are between pairs of elements, and when you attempt to see what the bracket is between D's and L's with respect to a natural basis, when you do that, these numbers that you get, so you always get such numbers, so often one calls such numbers as the structure constants. For the Lie algebra with respect to that given basis. Okay. So the structure constants that you obtain when you attempt to commute, so whenever I have a bracket, I often say you commute this with that. So when you attempt to see, so you calculate the bracket of D with L and you see what the structure constants are. Okay. And you collect together the set of structure constants. That set is often called delta minus. Okay. And this is, well, let me also mention the other words. These are often called the set of negative roots. Okay. So given any such Lie algebra, you can calculate brackets of D's with L's and obtain certain numbers, the structure constants, okay, often called negative roots. And similarly, so this is one side. In addition, you also have a natural group always acting on the diagonal portion. That's called the while group. So this is ingredient 1. Point 2, there's always a group, a finite group called the while group, which acts on the diagonal portion. And with these two ingredients, there is always an identity. So, and point 3, there exists an identity coming from this Lie algebra, which looks almost exactly like that. It says you take a sum over this particular group W of sine sigma e to the sigma rho minus rho is product 1 minus e betas, where betas range over that space, that set of structure constants. Okay. You can do, and I mean, notice I didn't say anything about rho. There is also a rho. So in general, whenever you have, from those, just like with the xi's, we figured out what the rho was. It was a certain combination of the xi's. In general, you can do the same thing. Given the structure constants, you can always figure out what that fellow rho is. Okay. So there's always such an identity associated to every finite dimensional semi-simple Lie algebra. And if you unravel this identity for the Lie algebra SLN, it gives you exactly the Vandermonde determinant identity. Okay. So for the Lie algebra SLN, this becomes the Vandermonde determinant identity. So there are several classical identities like these which will come from various Lie algebras. So for instance, we have seen one, you can do, so I'll just mention one other. So there are other Lie algebras. So here for instance, if I take the Lie algebra called SO to n plus 1, which is instead of all matrices of trace 0, you only take what are called the orthogonal the Lie algebra, or so this is basically all skew symmetric matrices. Okay. So this is just skew symmetric matrices. And you play the same game with it, meaning you figure out how it decomposes into 3 parts, you calculate the structure constants with the diagonals with the lower triangular, you obtain the roots, meaning the structure constants, you obtain rho, and you write out that identity. What it ends up giving you is the following. Then here's the identity. The product side looks like, it's sort of like Vandermonde with lots more stuff to it. Zi over Zj, I less than j, product 1 minus Zi Zj, I less than j, product 1 minus Zk, k goes from 1 to n. So that's the product side of the identity. Okay, you can see it's sort of a bigger generalization of the Vandermonde. The Vandermonde would sort of only look like the first part. Now you also have other combinations of the z's sort of coming into play, and so on the sum side you have a sum over a group which is bigger than just the symmetric group. So it is actually what we would call the semi-direct product of this with, so let me just write this here without saying too much more. Okay, so there will be a similar identity which you will get by playing with this Lie algebra, which tells you how that product becomes when you write it as a sum. Okay, and so on. So there's lots, there are several other Lie algebras. In fact, the full list is known, and all you have to do is just take your favorite Lie algebra and you'll get you'll get an identity. Okay, any questions so far? Yes? Excellent question. Yes, I didn't say anything about it. In general, there is a way of defining the sign, because these are not arbitrary groups, but they turn out to be what are called reflection groups. So there is a notion of, they are generated by reflections, and you think of a reflection as being of sign -1, just a single reflection. Products of 2 reflections will become sign +1 and so on. So these groups they also come with a sign. Okay, so my point so far is that to each Lie algebra you get an identity. Okay, and for SLN it just becomes our familiar Vandermonde determinant. Okay, but that's not quite all there is to the story. So it turns out one can actually do more with this. So one can actually try doing this in infinite dimensions. So what does this mean? So I want now to construct a vector space over the complex numbers that is infinite dimensional. And so I will just do it by example again. So remember SL2. So SLN in general is supposed to be all n cross n matrices of trace 0. So 2 cross 2 trace 0 matrices with entries in the set of complex numbers, right? That was our definition of SL2. Now, I am going to define something called SL2 hat, which is, well, I will try and copy more or less the same definition. Take 2 cross 2 matrices, trace 0, but remember I want to get an infinite dimensional complex vector space. So I will not restrict my entries to belong to C. I will say, well, I will now allow polynomials in one variable. Okay, so let me pick a variable. So let T just denote some variable. So I will say, well, I will take 2 cross 2 trace 0 matrices with entries which are polynomial in T and T inverse. Okay, so what do I mean by that? What's an example of a matrix which belongs to this space? Well, I can take T to the 6 minus 3 T to the minus 9, I don't know, T cubed 0 So here's an example of a matrix which would lie in my space. Right? Every entry should be a polynomial, meaning finite sum or finite linear combination of powers, positive or negative powers of t. That's what I mean by this. Yeah? Trace? Can't be too intelligent on the spot, I guess. Yes. Okay. So that's the definition of SL2 hat, and the bracket is the same. So you still define bracket of two things as AB minus BA. Okay. So there's no problem at all. Why do I want this is a much longer story, so I can't really go into that part, but let me broadly answer it. See, remember, I'm trying eventually to say that I want to get identities from Lie algebras. And now one set of, one place it comes from is if I have a finite dimensional semi-simple Lie algebra, I get some identities out of it. There is some structure theory, there is something which makes it work in that case. I want to see whether I need that same thing to work in the infinite dimensional case, right? So I should try and generalize it in a way where I can actually get the same structure theory or the same representation theory and so on. Now, in order to do that, I need the T inverse. If you don't have it, you can't quite generalize it. You won't get your identities and so on. So that's the reason. So that's sort of a much deeper question. So SL2 hat is for now the same bracket, AB minus BA. But I need to do to this I need to sort of add a two-dimensional space. Okay, so I'll call. So by that it's called K and D. Okay, so for people who have heard about these things, so K is so often this is what's called a central extension. So you define some. Here's your first guess for your Lie algebra, and then you need to do a little more by adding one further central element. Okay, so this is what's usually called performing a central extension. Okay, and the D is more or less cosmetic. One doesn't need it. Well, I guess it depends on point of view. So anyway, so the D is often what's called a derivation. So there is something a little more you need to do, but for all practical purposes, you can really think of this as being the heart of the Lie algebra. And it turns out that this guy has much of the same properties that just the ordinary SL2 has, okay, which is that you want to be able to decompose it into those three pieces and be able to get identities out of it. It turns out you can quite ordinary SL2 had diagonal matrices, lower triangular, upper triangular, and so on. SL2 hat also has lower triangular elements, upper triangular elements, and diagonal elements. Now, where of course you should say what these things mean. So, for instance, what would we define to be the diagonal elements? Well, it's defined to be you take just the usual diagonal elements of SL2, meaning constant matrices with complex numbers of trace 0, diagonal matrices with constant entries of trace 0, and to that you add in these two extra degrees of freedom that I threw in. So K and D also are considered diagonal elements. Okay. So this is your space of diagonal elements inside SL2 hat. The upper, well, I only care about lower triangular for now, because remember this and this, the structure constants obtained when you try and interact these two things together. Those structure constants are the ones which appear in your identity. So let's worry about D with L. So what are the lower triangular elements? So in a sense, there are sort of two notions of lower triangular or negative that are available to us. So one, we could say, when would you consider something lower triangular? Well, if it's a low in this infinite dimensional Lie algebra. So firstly, notice this is an infinite dimensional Lie algebra. I forgot to say that. So I'm going to think of this as being as a vector space over the complex numbers. So if I am going to allow powers of t, this is an infinite dimensional space, right? Because all powers of t are there and they are all linearly independent over the complex numbers. So this is surely an infinite dimensional space, and it's a Lie algebra as well. Now, so what would I want to define as my lower triangular elements? So there will be two classes of lower triangular elements. Things which are lower triangular already in SL2, where this is now some complex number. This is an element which is lower triangular in SL2 itself. Okay. So that we will automatically call, we will keep that as lower triangular. Now what else is lower triangular? So observe, we have the other notion of negativity. I am adding both T and T inverse. So maybe somewhat partial answer to your question comes up now. So I have T inverse, right? So those are sort of the negative powers of T. I can think of those as somehow also being in the lower triangular component. So what are the other lower triangular elements? Well, I'll think of anything in which all four are polynomials only involving powers of T inverse, strictly involving, T inverse, T to the minus 2 and so on. Only negative powers of T should appear in it. Okay. Such fellows also you think of as somehow being in the lower triangular component. Okay. So these are the two kinds of things which are there. Together they are the space of, they constitute the space L hat, and so I should say polynomials only in T inverse without constant term. And so there is an obvious basis that you can pick here. Don't I need, absolutely right, yes, trace 0. Thanks. Okay. So now I can try and do the same thing again. I want to try and figure out what D hat and L hat. Now what structure constants do I get? D was only? Yes, only 2 cross 2 complex. Diagonal matrices? Yes, D is the D for SL2. Which means only the scalar, the matrices with complex entries. Okay, but then notice I actually have 2 more degrees of freedom. So what is a typical element in D hat going to look like? So it's going to look like, well, it will be, well, actually minus x1. This case, okay, that's a typical element in my space D hat, and for L hat you need to pick a clever basis. So you need a basis to be chosen for L hat, and so again, just given the description of L hat, you can see that there is an obvious basis. You can choose 0, 0, 1, 0. That will give you a basis for the L portion, and then for L hat, you're only allowing negative powers of T. So you do the following: you take any number n at least 1, and you look at, for example, 0, T to the n, T to the minus n, 0, 0, or you look at things of the form, or you look at T to the minus n, minus T to the minus n, 0, 0. So you can sort of quickly write out a basis, a nice basis for L hat, because I've told you explicitly what L hat is. Okay, and then it's just a matter of taking an element from X and trying to see what its bracket is with an element from here. Okay, and when you do that, let me just tell you the answer, because I haven't quite told you everything about the central extension and how you do the bracket. So here's the answer. So what are the structure constants? What do you get when you hit D's with L's? So the structure constants now look like, remember the structure constant should, well, in the earlier case they involved x1, x2, x3, and the earlier case they involved x1 and x2. Only the diagonal entries were involved. Now they will involve x1, x2, x3 and x4, and here's the answer. There should be infinitely many of them because there are infinitely many basis elements. So here are the here's the list. There is, so they look like this: x2 minus x1 minus n x3, okay, where n is at least okay, I should be a little careful, so look like, okay, so let me just say n x3, n at least 1, x1 minus x2 minus n x3, n at least 1, minus n x3, n at least 1. So these are the things, structure constants, that you will get when you hit x's with the various basis elements I wrote. So this guy here will give you, x1 minus x2 minus n x3. That's what you get when you hit it with this. This guy will give you the other one, x2 minus x1. This fellow will give you the minus n x3. Okay, and remember there's one extra fellow, 0, 0, 1, 0, which is the thing which came from L itself. So that will also account for one more structure constant, so which will turn out to be just x2 minus x1. So this is the complete list of structure constants that you get when you try and commute D's with L's. Okay? And often one sort of combines the first and the last in one stroke. So you might as well just allow. So let me just do this. Okay, let me not quite remove it from your view. Just strike through. So instead of this, I'll put it in here and write n minus 1 x3. Okay, so that when n goes from 1, I also have a zeros involved. And notice x4 is not involved. You don't actually get x4s. Okay, now it turns out that this Lie algebra SL2 hat also has, well, it's close enough to SL2, the sense that the structure and representation theory is close enough that you can derive the same kind of identity. So there is actually an identity also for the case of SL2 hat. So what does the SL2 hat identity look like? Okay, so let me just write the product side first. So the product side was supposed to be a product over things of the form 1 minus e raised to beta, where beta was running over the structure constants. Beta runs over what I call the set of negative roots. Right? So now I figure out what structure constants are. There are infinitely many of them. Okay? So as you can see, it's going to become a product. N goes from 1 to infinity. So the first structure constant will look like 1 minus e to this whole thing, where n goes from 1 to infinity. Okay? So I'm just going to rename some variables. To sort of make it more compact. So this product side becomes exactly this, where what are my variable names? Z I've chosen to be e to the x2 minus x1. Q is e to the minus x3. So you just make these two substitutions, and then this entire list can sort of be written out more compactly like that. Okay? So it's now a product over all these guys. And the sum side of the identity, by a similar token, so the sum side starts looking like it's now a sum over a group. It can be rewritten as a sum over the integers of So this is something which I haven't really told you too much about, how, what the terms look like in the sum side of the identity. I mean, except for that sigma rho minus rho. If you sort of unravel it, in this case, this is what you get. So therefore, for SL2 hat, what's the identity? Product equals sum is your identity for SL2. Now the product side is this product. It turns out that this particular identity, that this equals this, was known for a very long time. This is a very famous identity called Jacobi's triple product identity. It's discovered by Jacobi somewhere in 1829. Now the Lie algebras that I am talking about, these infinite dimensional Lie algebras are sort of more modern origin. They are called Kac-Moody Lie algebras, which were discovered around 1967. So the Lie algebras are a sort of more modern discovery, whereas the identity which came from, at least in this example, if you take this Lie algebra SL2 and you unravel what its identity looks like, you get something that was discovered by Jacobi, back in 1829. I mean, this is the triple product identity, and in fact this was used by Jacobi in his work on theta functions and so on. So again, okay, there's one more name I want to mention, Euler. So for example, using this triple product identity, you can, as soon as you have an identity that product equals this sum, you can play with it. For instance, you can substitute various values for z and q and see what it becomes in those cases. So for example, there are some obvious corollaries to this. You can substitute. So let's make some nice substitutions. Wherever you see a z, you substitute q. So you put z, instead of z you put a q, and wherever you see a q, you replace it by q cubed. Okay, so you replace z's by q's and q's by q cubes. Now when you do that, so for example, let's see what you get in when n is 1. This looks like 1 minus z, so that's just a 1 minus q. If n is 1, you will get 1 minus q to the 3 minus q. So this is 1 minus q square, and this is going to be 1 minus q cubed. So if n is 1, this became 1 minus q square, 1 minus q cubed. If n is 2, you will get 1 minus q to the 4, 5, 6, 7, 8, 9, and so on. So when you sort of do this, the product side will become just product over all powers of, and the sum side will of course become whatever it becomes under this substitution. So okay, this is what you get, and this itself is, this again, it predates Jacobi's identity itself. So this is called Euler's pentagonal number theorem, which Euler discovered somewhere in the 1700s. Okay, so his proof was of course different, but once you had Jacobi's triple product identity, you could get it as a trivial corollary. Now the reason I mention is, well, the reason I wanted to mention this is this particular function, this particular infinite product 1 minus q to the n is rather important in number theory. So we call it phi of q. It's called Euler's phi function. Okay, so this is the Euler's phi function. You can think of it as a function of the complex variable q. It converges if q is in the unit disk and so on. So you can sort of play with it analytically as well. Now what you can think of this theorem as telling you is telling you an expansion of the phi function. Tells you what you get when you expand the phi function. Now Professor Surya Ramana this afternoon will talk about something on partitions of a number, and it turns out that the phi function is very closely related to the problem of understanding partitions. So let me just mention this. The phi function appears in several places. So if you take 1 over phi q, meaning you compute 1 over this product, and you try to expand this in powers of q, and the coefficients are precisely things that Surya Ramana will talk about this afternoon. They are just the number of partitions of k. So this is k going from 0 to. So this number p of k is the number of partitions. Okay, so the phi function is interesting. In fact, the inverse of the phi function is also very interesting. It's what's called a generating function for the number of partitions. But in fact, there are other powers of phi which are also very very interesting. So, for example, you know just like we made that particular substitution in the Jacobi triple product identity, you can actually just put z equals 1 in the Jacobi triple product identity, and what you will end up getting is a certain identity for the cube of, so I won't quite write it out, you will get an identity for the cube of the phi function. Okay, so all this stuff is very classical. Once you had things that were done pretty much after Jacobi discovered his identity, you can just play with them and you get various identities, things for phi cubed, like I said 1 by phi q is related in other places. But then all of this is, so like I said, the Lie algebras themselves were discovered only around 1967, and all this is only what you get. So from this point of view, if you take that Lie algebra SL2 hat and you unravel its identity, what it ends up giving you is Jacobi triple product. Okay, but the nice thing with this modern way of thinking about it, well, there are several other such Lie algebras. Right? Remember, just like SL2, I also have SL3, which is, well, something of dimension, what's SL3? Dimension 3 square minus 1. This is an 8-dimensional Lie algebra. SL4 is a 4 square minus 1. SL5 is a 5 square minus 1 dimensional Lie algebra. Right? I have several more. I have SO2n and so on. Now, to each of them, there is a hat. So I can do this infinite dimensional business starting with every one of them, and when I do that, I will get several more identities. Okay, and these were not known to Jacobi. Right? These are a very massive generalization of those identities. Now, when you try to do this with SL3, what it ends up giving you is an identity for the 8th power of the Euler phi function. This gives you an identity for the 15th power of the Euler phi function. This gives you an identity for the 24th power of the Euler phi function. As certain, it'll turn out that this is a double sum, this is a triple sum, this is a sum over 4 things and so on. Okay, so but each of them is just trivial to unravel once you have this bigger, the modern way of thinking about it in mind. Once you have the Lie algebra in mind, then you just figure out structure constant, the while group, blah blah blah, just plug it in, you will just get the identity out there. And all these are new. Okay, all these were discovered by MacDonald around 1972, not quite using the Lie algebras, but something very close called the root systems. Okay, now, so one has all these identities. Now, I guess do I have maybe a couple of minutes? Okay, so I just want to mention one other thing. So I'll just, okay, so here's something of a coincidence, this very last identity. So at this point, what we have is, we have lots of new Lie algebras and lots of new identities therefore, right, concerning very classical objects, powers of the Euler phi function. Now, phi cubed to the 24, so this is sort of a very strange coincidence that the Lie algebra SL5 has dimension 24. Therefore, one has an expansion for phi cubed to the 24 popping out of this theory. Now, it turns out that this particular guy, the 24th power of the phi function, is something that Ramanujan studied much before all this happened. So this is the famous tau function of Ramanujan. So he said the following, as usual, he picked some very strange powers and said stranger things about them. So if you expand the 24th power of the phi function, you write out the expansion for that guy. You call the coefficients as tau of n. Okay, so it's tau of n q to the n minus 1. Then he just wrote down sort of a very long list of extremely difficult to believe conjectures about tau of n. So for example, he said if you take a product, so this is what's called multiplicativity in number theory. If n and m have GCD 1, he said something about, some congruences. He said tau of n is congruent to, it's called the 11th power of the divisor function modulo 691. He said something about the growth. Okay, and several other such extremely difficult to believe things, all of which turned out to be correct. And this last thing was an extremely deep fact, which was finally proven as a result of the proof of what are called the veiled conjectures, sometime in, I think, 1970s. Okay, so this turned out to be an extremely deep fact. And so quite a bit of this, so in some sense, the tau function, or the 24th power of phi q, already had a rich history. It just very coincidentally turned out to be the identity coming up from SL5 hat. And so I promise this will be the last thing I'll say. So therefore, kind of these two things sort of merge together. If you unravel what, so here is one other expansion of the 24th power of the phi function coming from Lie algebras. Here is, and of course those coefficients are called tau of n, which have other properties. So you sort of marry these things together, and as a corollary, you actually get an expression for tau of n by comparing these two expressions. Okay, so there is an expression for tau of n, which I will just write out. It's a sum over, well, it's actually a sum over a 4-dimensional lattice. So it's over all 5 and satisfying some other 2 conditions of, so ui minus uj, I less than j, and there's some scaling factor. Okay, so if you sort of marry these things off together, then here's the final expression for the tau function. So this is only a finite sum. So the conditions look like the sum of the squares of the numbers should be 10n and so on, and there's some congruence condition. So this is a finite sum, because this condition makes it finite, of, well, Vandermonde determinants. Right? So what you finally have is an expression for tau n back in terms of the Vandermondes. So I guess I will actually stop there.
Thank you, Viswanath. That was a fascinating talk. Are there any questions from the audience? Yes.
Are we sure that we would get different identities by considering different Lie algebras?
Yes, yes, yeah. Because for one thing, the summation, you can figure out, so this number here is going to be the dimension of the underlying finite dimensional Lie algebra. That's not unique. You can have two different fellows of the same dimension. Okay, but if you start with 2 different Lie algebras of the same dimension, they give you 2 different expansions for 2 different expressions. They of course should turn out to be the same thing finally. Yes, you will get different ones, and I mean that comes from the actual form of the expression. If you actually write it out. Yes.
Are there any more questions? Well, if not, let's give Viswanath a big hand.